morning, everyone. So today we'll continue to talk about Python basics. So I have shared my screen. The last time we talked about there are four basic compound structures in Python: lists, tuples, dictionaries, and sets. And last time we talked about lists and tuples. Let's briefly review the definition. The lists are mutable ordered collections of data. Mutable means you can change the contents of a list. You can add or remove elements of a list. You can also change elements of a list. And tuples are similar to lists, but they are not mutable. They're immutable. You cannot change the length and the contents of a tuple. And for lists, when we create a list, we use square brackets. And when we create tuples, we use regular parentheses. Right? And both of these are ordered. If they are ordered, then we can use the position or the index of element to extract them, right, to identify them. Or it makes sense to sort the result. Okay, if the elements are not ordered, then it doesn't make sense to sort them at all. And the third one is dictionary. Dictionary is a collection of unordered mappings, key value mappings. So we'll start from here. So for example, we can create a dictionary called numbers. It has 3 elements, 3 pairs of key value pairs. So see, usually we use character string as the key. Right? So 1, 2, 3, these 3 are keys or key values. And then the integers 1, 2, 3 are the values in each pair. And we use colon to connect them. So if we do this, and let's print it. So this is a dictionary called numbers. Right? And items in a dictionary are accessed and set via the keys in the dictionary. So remember, dictionaries are not ordered. Elements are not ordered. So if you want to identify or extract or access elements in a dictionary, you need to refer to the keys, the key values. For example, if you want to extract the value of the second component or the component with key value 2, then you use the square bracket for 2. Then the value will be returned. Okay. So it's kind of special. You cannot use position to extract elements. You should use the key values. Then let's see, you can also add new elements into a dictionary. Dictionaries are mutable. You can add or remove elements. If you want to add a new element, you just need to use this kind of assignment equation. Create a new key and the corresponding new value for the key. Then after this, the numbers dictionary has one more element, one more pair at the end. Okay. So this is the new one. And just keep in mind that dictionaries do not maintain any sense of order for the input parameters. So they are not ordered. And it is designed in this way so that random elements access is very fast. So this is intentionally designed in this way. So the elements are not ordered. Okay, so this is dictionary. Dictionaries are useful, for example, when we transform data. If we want to transform categorical variables into integer variables or numeric variables. In machine learning, actually, many machine learning models do not accept categorical variables with character labels as their values. We have to convert them into integers or some other numeric values. In that case, we can create a dictionary as a mapper and then transform the categorical variable into numeric variables. We'll see some examples later next week. And then let's move on to the last type, sets. So the sets contain unordered collection of unique values, unordered collection of unique values. And so this is also unordered. And we usually use curly brackets to wrap elements in it. For example, we created a set of prime numbers, call it primes, like a few prime numbers. If we run this, get this, right? No problem. What if we create a set with repeated values? For example, this odds set has 2 ones. It seems that there is a conflict. What will happen? Let's see. Apparently, the repeated value is removed. Only distinct values are kept in the result. Even if we force in a repeated value, it will be removed. Right, so this is set. And as we have learned in other courses, like elementary statistics courses, there are some set operations like union, intersection, difference, symmetric difference. So this one is kind of new for some people. Let's take a look at each case, each operation. Union. So union is a set of, is a collection of elements of everything. Right? It's like you pour 2 sets of elements together. Right? So if we draw a Venn diagram, union will be like this. You have 2 sets. Union contains everything, the whole thing. And an important feature is it does not contain overlapping elements, right? So it will only keep 1 copy of the overlapping area. So any repeated values will be removed. So in Python, we can use this bar operator to calculate the union. Remember, we created 2 sets, primes and odds. Let's get their union. So see, this is the union. Contains the distinct values in A or B. In A or B. Usually in statistics, it is denoted by A or B or A, U, B, right? This is union. And Python also has a method, a union method, dot method. So for example, you can take primes and then dot union odds, you'll get the same result. Similarly, you can take odds and then dot union, get the same thing. So apparently, the union operator is symmetric. It doesn't matter which set goes first, which set goes second. It doesn't matter. So this is a symmetric operator. And move on to intersection. Intersection contains the common elements of 2 sets. Common elements. So this is intersection. Denoted by A and B, or A cap B in statistics or probability, right? So in Python, we can use the AND operator. it will find the intersection. And there is also a method, just called intersection. You can take one set and dot intersection the second set, get the same result, right? And if we start with Oz, get the same result. So again, this is a symmetric operator. It doesn't matter which set is specified first. Okay, and the result you see, the results, the elements in the set is ordered automatically for you in ascending order. Next difference. So what is the difference? So a difference between A and B, if we denote it in this way, right, it will remove the common elements of A and B from A. So if we draw a Venn diagram, it will be very clear. Because it will have two sets, A and B. A minus B is A. Okay, take A and get rid of the common area, or the overlapping area. So this is A minus B, or A, just write it down, A minus B. So in Python, it's very simple, just use the subtraction operator. Primes minus odds, see, 3, 5, 7 are all odd, right? Odd numbers. So only 2 left. So this is primes minus odds. And there is an operator, method in Python too. It's just called difference. Same thing. Apparently, this operator is not symmetric. If we take B first, and then minus A, take B and get rid of the common elements of A and B, then we will have this area, okay? Apparently, they are different, quite different. So this operator is not symmetric. So for example, let's see, if we start with Oz and then dot difference primes, we get 1, 9. Starting from Oz, get rid of prime numbers. So 3, 5, 7 will be removed. Only 1 and 9 are left. And the repeated values will be got rid of. So only 1 and 9 left. Yeah. So this is difference. The difference operation is not symmetric. Now, last one is symmetric difference. So this one, from this name, we know that must be symmetric. The operator is this hat operator. So let's see. If we run this, we get this. So what is symmetric difference? Let's draw a Venn diagram. Clear. It contains elements that are in A or B, but not in both. So it represents the combination of these two areas. Basically, A union B minus A intersect B, right? So this is symmetric difference. From the definition, you see that this must be symmetric. The result will not depend on which set goes first, right? And the method is called symmetric underscore difference. You got the same thing. And let's test if it is indeed symmetric. We take odds first, and then symmetric difference primes. Got the same thing. And notice that the results, no matter what, they are ordered in the same way. Although sets are not ordered, but elements are automatically ordered for you. When you see the result, they are automatically ordered for you. All right, so that's That's all about the four types of compound data structures. And Python has some other data structures, and you might find useful. You can check the documentation of Python for more types of data structures. Okay. All right, that's all for this small session. Any questions? Okay. Let's move on to session 4. So session 4 is about NumPy data structures. We're talking about various types of arrays or variations of arrays. So session 3 is about compound structures, which means data, the elements in this data structure can be of different data types. Okay, so they are called compound structures. But in this session, we talk about NumPy data structures. For all of these data structures, the elements should be of the same data type. Namely, they are all numbers, actually. Okay. But they are quite useful because most of the machine learning models in Python assume that the input data sets are NumPy arrays, many of them, NumPy arrays. And the result, the output, is also a NumPy array. So that's why it's kind of important. Let's study there's different types of data structures in NumPy and also features, operations about them. Okay. So the NumPy package is the foundation of the Python machine learning stack. It allows for efficient operations on the data structure, often used in machine learning. Vectors, matrices, and tensors. Tensors are array-based homogeneous data. Because they are very homogeneous, it's more efficient to work on them. First, let's load the NumPy package. So in Python, whenever we load a package or library, we use this kind of syntax. Import the package name as a shortcut name or an abbreviation of the package name. You don't have to do this. This is not necessary. The reason that we always create an abbreviation for a package when we load it is because later on we need to refer to the library whenever we use a function in the library. We use a dot syntax. For example, if we use the maximum function in NumPy, we will use the function will be referred to np.max. Okay, so we have to refer to the library. If we import a library in this way, we have to refer to the library name. So in order to save time and effort, we want to create a short name for the package. That is the whole purpose of creating this abbreviation. Okay. Let me first run this. Otherwise, it won't work. So first, basic data structure in NumPy is a vector. It's a vector. So first, let's take a look at row vectors. To create a row vector, we use np.array, the array function in NumPy. And the parentheses are used to call a function we have learned last time. And this is the content of the array. So 3 numbers. We list them in a list. You have to use this kind of syntax. Don't ignore these square brackets. You put a list within the parentheses as an argument. Then we create a row vector. It seems that this is very similar to a list, right? The only difference is that you see there's no comma in between any pair of values, right? So no comma. This is a row vector. Then let's see how to describe a row vector. Vectors are one-dimensional. We can check the actual dimension of a NumPy object using the ndim method. This is a dot syntax because it's a one-dimensional object. So the number of dimension is 1, which is really good. You can also check the length of a row vector using the len function. It returns the number of elements. You can also check the shape of a row vector. Three, nothing. Because it is only one-dimensional, you only need to use one number to show the number of elements. So 3, it still saves the space for other dimensions, but row vectors are one-dimensional, so one number is shown. Then column vectors. How to create a column vector? We still use the array function in NumPy. And now you see we use a kind of nested list. So in the list, each element is also a list. 1, 2, 3. Although there is one single value in each small list, but it's still a list. So each list represents one row in the column vector. Because this is a column vector, there's only one element in each row. So this is a column vector. And now let's check the dimension of a column vector. It's actually a 2-dimensional object because it's literally a matrix with only one column. So it's different from a row vector. You can check the length of it. Still, you can also check the shape of it. So now you see we have 2 numbers in the shape. Number of rows and number of columns. 3 rows and 1 column. So from this example, you see that column vectors are actually 2-dimensional objects. And it is the main data structure in NumPy. So the main data structure in NumPy is multi-dimensional array, just as what we have seen now, multi-dimensional array. And the array. All right. And next, matrices. And matrices are 2-dimensional arrays. We can still use the array function to create a matrix. Let's see, we have this kind of nested list in the argument part, and each small list represents a row. So this will create a 3x2 matrix, 3 rows and 2 columns. And how to describe a matrix? By the way, we actually can use a function called mat to create a matrix. So this is a function in Python that is in NumPy that is used to create a matrix specifically. We get a matrix. However, it's recommended to use the array function instead of a mat function. Because if you use a mat function, you create an object, which is a matrix, right? So, but we know that in Python and also machine learning, the main data structure is NumPy's n-dimensional array. It's not a matrix. It's not a matrix. So it's better just use the array function to create a matrix. The result is the same, just the type of object is slightly different. All right, describe a matrix. Let's check the shape. The shape, of course, is the number of rows and number of columns. So it's a vector of integers, 2 integers. And we can also check the size of a matrix. The size is the total number of elements in a matrix, namely the number of rows times the number of columns. So M2 has 3 rows and 2 columns, so the size is 6. And we can also check the dimension of a matrix is 2-dimensional, which is similar to the column matrix. All right. Next small topics is compressed sparse matrix. So this is kind of special in Python. So a common situation in machine learning is that we have a very big data set. However, most of the elements are zeros. Most of the data are zeros. For example, imagine you have a matrix where the columns are every movie on Netflix and the rows are every Netflix user. Then you can imagine that there are thousands of columns, even 10,000 columns, because there are so many movies in the history today. And there are a lot of rows as well. But for each customer, right, each user, Netflix user, most of the entries are zeros because our life is length of life is so limited. We cannot watch so many movies. So for most of the entries for each user, there are zeros in it. Okay, so this is a typical scenario in machine learning. This is called a sparse data set or sparse matrix. If we want to save the matrix as it is, then it will occupy a big space in memory, and you can imagine the processing will be kind of slow. Right? So to deal with this situation, we actually can compress this kind of sparse matrix, namely using just very limited amount of information to represent the entire matrix. For example, we have a matrix called M3, and it has 3 rows and 2 columns. Sorry, 10 columns, but notice that only 2 numbers are non-zero. The rest of them are all zeros. So this is a typical example of sparse matrix. Of course, this is a toy example, and the data set is not too big. In practice, it could be very big. And in this case, we can create a compressed sparse matrix using a function in SciPy. SciPy is another package that we can, so SciPy contains some mathematical and machine learning and data processing functions. And in particular, it has this sparse function, sparse module. So from the SciPy package, we import the sparse module. So it's kind of like a sub-library, which contains some functions. Right? And then we call this function CSR matrix. CSR stands for compressed sparse row matrix. So it will summarize data along the rows. For each row, it will count how many elements are not zero and the values of the non-zero elements. Okay? So let's compress M3 and save the result in M3 sparse and see the result. Okay? So you see it shows you the coordinates of the non-zero element and also the value of the non-zero element. So we go back. Let's see. So this element has index 1, 1. Remember, Python is 0-based. So 1, 1. And 3 has index 0, 2, 0. And the third row, the first column, 2, 0. So that's why 2, 0, 3. So apparently, if we store the data set in this way, we save a lot of space. This is a special case. If you have a sparse matrix, you have the option to compress it into a compressed sparse matrix. And it's possible to convert it back to the original one. We will see one example later when we talk about machine learning. We'll talk about data processing. All right. Any questions so far? Okay. Next small topics is subsetting objects or data structures in NumPy using NumPy functions. So for vectors, row vectors are one-dimensional. So you only need one index to select an element, extract the first element using this. It's similar to the case when we extract one element from a list or a tuple. We use square bracket. And if we want to select all elements, then we can use this. Column means everything. And we can select everything up to and including the third element using column 3. Remember, this 3 is the index of the fourth element. So up to 3, but not including 3. Okay. So 0, 1, 2. These are the indexes of these 3 elements. Okay. The point is you can omit the first index if you will start from the very beginning. Similarly, if you want to choose everything after the third element, then you can do this, starting from 3 all the way to the last one. After, because this 3 is the index of the fourth element. So this is the fourth, fifth, sixth elements in the array. Don't be confused. It's a zero-based indexing system. You can also use a negative index. For example, -1 is the index of the last element. So these are very similar to lists. Matrices. Matrices are two-dimensional objects or arrays. So if you want to select an element, you need to specify the row and the column indexes. For example, if we want to select the second row, second column, intersection of second row, second column, then we need to use M4, 1, 1. So this one is 1, 1. And we can also select rows. For example, select the first 2 rows and all columns. Then you can do this, comma 2, and then, column 2 and column. So notice that you have to put something in the column index part. You cannot leave it open. It's different from R. In R, you can get rid of this, but in Python, you have to put something here. And column 2 means 0, 1, up to 2, but not including 2, so the first 2 rows. Okay. And similarly, we can select the second column, one column, using this. Right? Because we select the second column, we should select all of the rows. Right? And the column is from 1 to 2, but not including 2. So namely, the column with index 1, which is the second column. So this is the result. So if you use this syntax, you will have a column vector. Exactly, the second column will be extracted. You might wonder why why not just use 1 here? Because we only want to select the second column. Why not just using the index of second column? Let's see. Turns out that if you use this kind of syntax, you will get a row vector instead of a column vector. So sometimes you may prefer to create a column vector. In that case, you need to use this kind of syntax. Right? All right. And then let's see operations on NumPy arrays. So NumPy arrays allow us to perform operations between arrays even if their dimensions are not the same. This is called broadcasting. So basically, it will do everything element-wise and try to make it work. So for example, we create a matrix M5 with 3 rows and 4 columns. And then we want to add 100 to all elements in the matrix. We can just directly do this, M5 plus 100. Okay. Although M5 is a matrix, 3 by 4 matrix, and 100 is a single value. It at most can be considered as a vector with 1 element, but apparently their dimensions don't match. But still, Python can accept it, and it will actually add 100 to each element to it. So this is called broadcasting. It will broadcast the smaller value, the smaller dimension value to the larger one. Right? Try to make them have a matching dimension and do the operation element-wise. It's similar to R. And we can also, for example, multiply each element by 10, then just use M5 times 10, which will also work. No problem. Okay. Very convenient. And next topic is calculate descriptive statistics. Yeah, NumPy has many functions that we can use to summarize data in NumPy arrays. And other packages also have similar functions. They may or may not have the same names, but they have similar functions. But now we're using NumPy functions, so that's why it's np.max. So M5 is a matrix which has 12 elements. If we apply the max function on it, it will find the maximum element in it. Remember, NumPy arrays are arrays, so all the elements have the same data type. Then it makes sense to treat them in the same way. They are basically equivalent, although they have different row index, column index, but essentially they are a set of data, a set of values. So it makes sense to calculate anything, any statistic from them. For example, the maximum. You can also calculate the minimum, which is 1. And there are also some statistics functions in NumPy. For example, mean, variance, VAR, and standard deviation, which is square root of the variance. So all of these are available in NumPy, and it makes sense to calculate them for NumPy arrays because they are essentially sets of values of the same data type. And for matrices, it makes more sense to calculate row statistics or column statistics, which is very common in practice, right? For example, if we want to calculate a column matrix, then you just need to add an argument, x is equal to 0. So pay attention in Python, in NumPy, 0 represents column. Right, and 1 represents row. Okay, column, row. So if x is equal to 0, then it will calculate the column maximums for matrix 5. This is matrix 5 and 5. Column maximum are 9, 10, 11, 12. Okay. Similarly, if you want to calculate row maximum, just specify x is equals 1. Then for each row, it calculates maximum. And this is a NumPy definition, row and column. But in other packages, for example, in Pandas, we will use this a lot in the next module. In Pandas, 0 is corresponding to row, 1 is corresponding to column. Right? So if you use functions in Pandas, then x is equal to 0 will be corresponding to rows, 1 corresponding to columns. So it really depends on which function you are using and where the function is from. So that's why usually we import packages in the basic way, and then each time we call a function, we still refer to the package that the function belongs to, so that everything will be very clear. We won't be confused. So for Pandas functions, we usually use pd dot something function name. All right. So this is row and column statistics for matrices, and you can also calculate, for example, column mean and the row mean. So anyway, basically, this is kind of universal. You can call a function and specify the axis to calculate column or row statistics. Very convenient. All right, next topic is reshaping arrays in Python. As I mentioned many times so far, NumPy arrays are sets of values, the same data type. So it makes sense to reshape matrices, just change the number of dimensions, number of rows, number of columns, and to reshape them. Right. So reshaping means we change the shape of an array without changing the element values. And it allows us to restructure an array so that we can maintain the same data, but it is organized as a different number of rows and columns. The only requirement is that the shape of the original and the new matrix contain the same number of elements. So for example, you can convert a 3x4 matrix to a 4x3 matrix, or 2x6 matrix, 6x2 matrix, or 12x1 vector, 1x12 vector. All of these work, but you cannot convert it to a 2x5 matrix. It won't work because the sizes are not the same. It's very intuitive. All right, let's see one example. So N5 is a 3x4 matrix, right? If you want to reshape it to a 4x3 matrix, then just call N5 and then call the reshape method using this dot syntax and specify the number of rows and columns for the new matrix. So see, this is the new one. Notice that the elements are filled row-wise still. 1, 2, 3, 4, 5, 6, all the way to the last one. The order will not be changed. One useful argument in reshape is -1. So this means as many as needed. So for example, reshape 1 -1 means I will reshape the current array into an array with 1 row and as many as columns that are needed. So this will help us to do the calculation. We don't need to figure out how many columns we need. As long as we keep the same size, then we should be okay. So let's see. if we reshape M5 to a matrix with 2 rows and some number of columns, we can do this. Right? Since we have 2 rows, then we must have 6 columns. Similarly, we can reshape it to a matrix with 1 row. And then there will be 12 columns. Okay. Notice that after we apply the reshape function, the result is still a 2-dimensional object. You see 2 layers of square brackets. So this means this is a matrix with 1 row. Its dimension, the number of dimensions is still 2. And there is another function that is similar to reshape 1 negative 1. That is flatten matrix, a flatten function. So this function will transform a matrix into a 1-dimensional array. 1-dimensional array. So let's see. Let's apply the flatten function on M5. Then this is a result. Notice that there is only 1 layer of square brackets now. So indeed, this is a row vector. It's a 1-dimensional array. So this is different from the reshape. Reshape will always make it a 2-dimensional thing. And flatten will make it a 1-dimensional. Okay. All right, next, transposing a vector or matrix. So transpose means, in linear algebra, it means we make columns to rows and rows to columns. Or the column and row indices of each element are swapped. Essentially, same thing. So for example, M5 originally looked like this, 3 by 4 matrix. And if we transpose it, we can use the dot method, capital T. In R is little t, but in Python is capital T. Right? Then we get this. You see the original columns becomes the rows now. Right? These 3 rows become the 3 columns. So this is transpose. So apparently it makes sense to transpose a matrix. So how about vectors? Can we transpose vectors? It depends. So let's see V1. V1 is the first vector we created. It's a row vector, 1-dimensional object. Okay. So suppose we want to transpose it. Let's see what happens. It won't do anything. It will still be a row vector. It cannot be transposed to a column vector. So basically, the transpose function does not have any effect on 1-dimensional arrays. Okay. And how about column vectors? So create a column vector using this function. Array, NumPy's array function, you see now we have 2 layers of square brackets. So this will create a column vector. Column vector with only 1 row, okay? And then we can transpose it. When we transpose it, we can change it to a column vector. So only if the original vector is 2-dimensional, it makes sense to transpose it. If originally it was a 1-dimensional object, then it doesn't make sense to transpose it at all. There won't be anything happening. Pay attention to that. And there are many other calculations about matrices in NumPy. We rarely need to deal with these, but just want to let you know that they are available in NumPy. They are all available. And the last topic in this small session is generating random numbers. So it's quite useful in practice, in like the data science and machine learning, to generate some random numbers. So in this small part, we will talk about different functions to generate random numbers from different distributions. Okay. So before we start, we set the random seed. This is because if you want to have the same result, you need to set the seed. So the seed is kind of like if you have used random number table before, the seed is somehow like the starting point, a fixed starting point. Right? After you set that, then later on, if you do some simulation, it will always give you the same result because the random numbers generated by computers are pseudo random numbers. They are generated by computer algorithms, so they are actually determined. Although they look random, they are actually determined. So there is a way to control their randomness, their performance or output by setting the seed. Okay, so for example, if you set the same seed with me, if you run my code, the same code, you get the same result. Although theoretically they are random numbers, still you get the same result. So this is the way to get reproducible results. Okay. So now the first function we talk about is generating random numbers from uniform 0-1 distribution. The function is just called random. The only argument you need is the number of numbers you want to generate. So for example, get this. Uniform, just as a uniform 0-1, the density curve is a straight line. So which means all the numbers in this interval 0-1 have the same chance of happening, same probability of happening. Density function is also 1 for x between 0 and 1, and 0 otherwise. So this is uniform. Right? So basically, it's like you draw 3 numbers from the interval from 0 to 1. That is uniform. The function is just called random. And yeah, next, discrete uniform. The function is called ran int. Okay, random integer. You specify the from and to, or the start and end, and the number of elements. So this one will generate 5 numbers from discrete uniform between 0 and 10. Discrete uniform is similar to continuous uniform in the last page, but now you have a distribution somehow like this. Okay, so you have a middle distribution curve. How like that? So basically, it's like generating numbers from discrete uniform, from a set of numbers between 0 and 10. Okay. And let's see how it works. Next is normal. So this function is used to generate numbers from normal distribution with mean 0 and standard deviation 1. You can also generate random numbers from Poisson distribution. So the first argument in the parentheses is the parameter of Poisson. It's the lambda, the mean. And the second is the number of numbers you want to generate. And last one is uniform. So this one is a generalized version of random, the random function in the previous slide. The random function can only generate numbers for uniform 0, 1, right? But if you want to have a different range of values, you can use the uniform function. For example, you want to generate 3 numbers from 1 to 2 on this interval instead, then you use the uniform function. Okay. That's this section, for this section. Very basic and trivial things, but I think it's still good to know. You have this class, so later on, people will assume that you know something about Python at least. Okay, so these basic things are not related to our class that much, but still we should know it. Okay. I've got a question. Can we name parameters using these functions? If in R we can state min equals x. Yes, we can change the arguments and we can name the arguments. Just search the function, Google it, and NumPy function, and then function name, and check the argument name. Sometimes they are not what we thought. So they have different names, but usually if we put the arguments in order, we don't need to specify the argument names. So that's kind of like a shortcut, but it's possible to specify their names. And also, of course, it's possible to change their values. For example, in the normal case, you can change it to like 115, for example. It doesn't matter. You can change them. But I'm not sure the arguments names probably mean a standard deviation. I didn't check. Haven't checked yet. All right. That's all for this section. It's longer than I thought. Now let's move on to session 5. So these are some coding components in Python. Because sometimes we want to create functions by ourselves, and it's good to know how to create simple functions and how to use simple functions in Python. So in this session, we will talk about that. So control flow, loops, and defining functions. Of course, our class is not focused on Python programming, so we will just learn some very basic things about creating functions in Python. Okay. First, conditional elements, statements, if, else if, and else. If and else are quite familiar for most of us, but else if is not. This is just stands for else if. Okay. But Python decided to combine them together, call it else if. Let's see this. So conditional statements allow programmers to execute certain pieces of code depending on some Boolean condition. So if some condition is true, do something. Otherwise, do something else. Okay, that's it. Conditional flow is like this, right? So let's examine each statements one by one. So first, the if statement. If because it's not in the function yet, let's first assign a variable, x equals -5. And if x is less than 0, colon, return, okay. Then indentation, a block of code, print -x. So the result is 5 because x is negative, is smaller than 0. So this is the simplest if statement in Python. Okay. Similarly, if x is positive, then nothing happened, right? Because you see the condition is false. Right? The condition yield false. So this statement is not executed. So nothing happens. So if you only have an if statement, you might not have the result, because if the condition is not satisfied, nothing will happen, right? So pay attention to that. And then if statement without an indentation will raise an error. So actually, if you strictly follow the rules, for example, type if and condition colon, then hit enter, automatically the indentation will be created for you. But sometimes you might accidentally remove the indentation, right? Then if you run this, you get an error, indentation error. So of course, most people won't do it. So if there is indentation, then it's okay. Right? This is the first note. And secondly, if you have only one statement to execute, you can put it in the same line. So if you only have one condition, and to check and one statement to execute if the condition is true, then you can actually put them in the same line. It's allowed. And then the second is the else if statement. So this one means if the previous conditions were not true, then this condition. So if all the above conditions are not true, check this, please. And then if it is true, do something. Right? So it's kind of like exclusive thing, right? To consider something else. So for example, A is 12, B is 12. If A is less than B, print A is less than B. Else, if A is equal to B, print A is equal to B. Okay. So consider this condition only if the previous condition is false. That's what else is. Else if works. So because A and B is equal to B, so that's okay. And the last one is else. The else keyword catches anything which is not taught by the preceding conditions. So sometimes you only have one condition to check. In this case, you only need one pair of if and else. If the condition is true, do something. Otherwise, else do something. Right? If you only have one condition, one scenario to check, then you only need a pair of if else. You don't need else if in this case. So for example, in this example, x is -3. If x is less than 0, y is equal to -x. If it is else, y is equal to x. So apparently in this if else conditional flow, you create a new variable y, which is the opposite of x. Which is the absolute value of x. Okay, and then print y. So x is -3, so it's negative. Y is equal to negative, or -3 is +3, right? So y is always equal to the absolute value of x. So this is one case if you only have one condition to check. If you have multiple conditions to check, then you will need else if in the middle, right? In the middle of if and else. For example, x is the pi, the constant pi with non-pi. Okay. So pi itself may not work, but np.pi is the pi defined in the non-pi package, which is the irrational. X is non-pi pi. If x is equal to 0, print x is equal to 0, greater than 0. Else if positive, then positive. Else negative. Okay. So apparently pi is positive. So this one works. It's true. Then the last one will not be checked. So this is the if else and else if. And sometimes when you write a conditional flow, you want to consider invalid inputs. In that case, you can raise errors. So in Python, you can use this keyword raise and then value error and then type the error message. So for example, if the input is invalid, for example, the input is a character string, apparently Python does not know how to compare a character string with integers like 0. In that case, the conditional flow won't work. So the first, in the first if statement, we can string out this situation. So if type of x is not an integer or float, is not a number, then raise an error. X must be a real number. Then the entire conditional flow will be ended. And if it is a valid result, then it will go through. For example, you see x is character string, then we actually raise the value error. So this will be useful when you create your own function. You want to string out invalid inputs. So at the beginning, you can add a if statement to raise value errors to remind the user of the function that your input is not valid. Think about it. And if we input a valid input, pi, then you will get a valid result. As this is not true, so this one will be skipped. This is raising errors. Okay. All right. Next. Yeah, pay attention that how we need to use colon and indentation to denote different blocks of code. And next, loops. Let's finish loop. Hopefully we can finish loops. Because in your homework, you will have 1 or 2 questions using loops. Okay. So loops are a way to avoid repetitions. If you know that a chunk of code will be run repeatedly in your program, you want to put them in a loop so that you can avoid repetition and your program will be shorter. So we'll learn 2 basic loops. First one is for loops. For example, this is a simple for loop. For I in the list with 5 numbers, 0, 1, 2, 3, 4, 5, print I and with empty space. So let's run this. Right. So this simple example shows you the basic elements in a for loop. So there should be so first in a for loop, we specify a looping variable. So in this case, I is the looping variable. You can use any letter to denote the looping variable. I, J, K, A, B, C, X, Y, Z, doesn't matter, right? Just make sure that you use the same letter in the loop when you refer to the looping variable, right? And then you need to specify a sequence you want to loop over. So in this example, the sequence is a list of values, okay? But actually it doesn't have to be a physically existing list. It can be an iterator. It's a conceptual sequence of numbers. We'll see a little later. And then we use the in keyword to connect the looping variable and the sequence of values. So which means in each iteration, the looping variable will take one value in the sequence, one after the other, exactly in this order, right? So I will change values from iteration to iteration. And then in the for loop, in each iteration in the for loop, the index variable, the looping variable usually will be called or tried or used somehow in a way, right? And it will be automatically updated because all the values are listed in here. So you don't need to manually update the looping variable if you use a for loop. Okay, so very simple. So as I said, the sequence does not have to be a list of specific values. It can be a conceptual range of values. For example, you can say range 10. So this is sort of like a list, but not exactly a list. It just represents the numbers between 0 and 10, not including 10. Okay. So it's up to 10, but not including 10. By the way, this n equals quote space will make sure that the outputs will be on the same line. If you get rid of this, let's try it. You will have a vertical column of values, which will use a lot of space. Of course, you might not want to do it. That's why, oops. Use n equals quote space. Single quote, double quote doesn't matter. And the range function is often used in Python. Okay, so it has 3 basic arguments: start, stop, and step. Right? So if you don't want to, so by default, it will start from 0. But if you want to start from other numbers, you can do so. For example, start from 1 and stop at 11, but not including 11. And step by default is equal to 1. So this is, we use the range function to create the contents of a list. I put it here. And the result of the range function itself is not a list. It's an iterator. Right? So we can also change a step to 2. Then we will create a list of even numbers. Right? So very flexible and useful. And next is nested for loops. So sometimes you might need to use this kind of loops. So there is an outer loop for I in A, B, C. And this is a character string. And for J in 1, 2, 3, 4, print IJ. So this example is used to show you the underlying algorithm or logic of a nested for loop. So basically, starting from the outer loop for I equals A first, I in the first iteration of the outer loop, I is equal to A. And then J is equal to 1, print IJ. So A1 will be printed. And then J will be equal to 2, right? I is still equal to A. And then, so the inner loop will be first finished for each value of the outer loop. So that's why the result is like this. So the outer loop, in the outer loop, I is equal to A, and then inner loop 1, 2, 3, 4, and outer loop I equals B, and then J 1, 2, 3. So this example just shows you how it works. Right? For each value of the outer loop, the inner loop will be done first. All of the iterations. All right, while loop. While loop is very simple. It will iterate until some condition is met. So for example, I is equal to 0, while I is less than 5, print 2 to the I, and 2 to the exponent I. And then we update I manually, we add 1 to I. So I starts from 0, and then 1, 2, 3, 4, until 5. And then this condition is false. Then the loop will be ended. So this is the result, okay, a for loop, a while loop. So apparently there is a difference between, there are some differences between a while loop and a for loop. So first of all, there is a condition. If the condition is true, it will run forever, okay? And there is no, so you don't have to have a looping variable. Of course, in this example, we have a looping variable. If you use a looping variable, then you need to manually update the value of the looping variable by yourself. Otherwise, it will run forever, right? And because the looping variable itself does not have a range, but a default range is not specified here or there. You have to initialize the value of the looping variable if you want to use a looping variable. So that is the difference between a while loop and for loop. But usually, if you have a looping variable in your mind, then just go ahead and use a for loop. Don't use a while loop. So while loops are usually used to deal with special cases. So this example is just for comparison purpose. You must update your looping variable by yourself and initiate it at the beginning of the loop, before the loop. All right, I think I have to stop here.